What if I told you that you, right now, are part of a 2.5 million year story? The story of humans teaching objects how to think. This is the day you ate the code "Know Me." It's the story of how our inventions evolved from simple tools to intelligent companions, and how learning to code lets you continue that story.
Intro.
ルームシャンブルズ
When do you think humanity's story with technology began? Was it when we invented the wheel about 5,500 years ago? Or when we shaped the first stone tools 2.5 million years ago? Neither is quite right. Our story with technology began the moment we learned how to count. Long before glowing screens and keyboards, we had only our hands, 10 fingers that became the base of our counting system. 10 digits. Traders marked tallies on wood and moved pebbles to track goods. Counting turned thought into something we could record, compare, and build upon. As societies grew more complex, fingers and tally marks reached their limits. Imagine trying to track the taxes of an entire kingdom or calculate trade between nations. Fingers and stones would fail quickly. That pressure gave birth to the first dedicated tools for calculation. The abacus, refined in China and used across Asia, arrived with sliding beads that let people compute faster and more reliably. It became the first great member of humanity's fleet of calculation. In principle, an abacus with n rods can represent values up to 10 to the power of n minus 1. A 9-rod abacus can show numbers as large as 10 billion minus 1, which is an impressive range. The abacus was powerful but still depended on human hands. Every bead had to be moved manually, and a single slip could throw everything off. But humanity's curiosity never stopped at good enough. As problems grew more complicated, so did our hunger for faster and more reliable tools. What if the machine itself could carry more of the burden? In 1642, a 19-year-old young man watched his father, a French tax commissioner, grind through endless tax calculations and decided there had to be a better way. He imagined a device that could handle the calculations itself, a mechanical machine of gears and wheels instead of beads and fingers. It was the Pascalin, built by the famous mathematician and philosopher Blaise Pascal. The Pascalin, a wooden box of gears and rotating dials that could add and subtract by turning its wheels, faster and more consistently than a weary human at midnight. But Pascal's work wasn't the end. In the 1800s, another genius, Charles Babbage, envisioned something even greater. A machine that could not only calculate, but also be programmed to follow instructions. He designed the analytical engine. His analytical engine was never completed, but the idea was revolutionary. A general-purpose machine guided by stored instructions rather than hand-cranked steps. In 1842 to 1843, enter Ada Lovelace. If Babbage drafted the ship, Ada was its first navigator. She studied his designs and wrote what many consider the first computer program, seeing beyond numbers to patterns, perhaps even music. Think of them as a visionary engineer and the mathematician who turned his blueprints into possibility. As centuries passed, our sails caught stronger winds. Mechanical devices proved useful, but they were still limited by gears and levers. Humanity needed a way to make machines faster, more automatic, and capable of handling vast oceans of information. By the late 1800s, the world met electromechanical data processing. Herman Hollerith's punched card system let machines read information to process the U.S. Census. The impact was dramatic. What had taken about 7.5 years for the 1880 count dropped to roughly 2.5 years for 1890. For the first time, information itself became something machines could ingest, transform, and return at scale. But every great voyage has its grand leap. Just as ships once moved from sails to engines, computation moved from gears and cards to electricity itself. The age of electronic computers had begun. What if I told you that the moment sparking the entire digital age didn't happen in Silicon Valley or a sleek modern lab, but in a dim basement filled with glowing tubes, tangled wires, and most importantly, the urgency of war? Would you believe it? During World War II, the U.S. Army faced a brutal time problem. Artillery firing tables took days to compute by hand or with mechanical devices. Engineers J. Presper Eckert and John Moschly proposed a radical solution, a fully electronic machine performing thousands of calculations per second. In 1945, in the basement of the University of Pennsylvania's Moore School, ENIAC roared to life. a room-sized vacuum tube Titan, and one of the first general-purpose electronic computers. The era of electronic computation had begun. A famous anecdote from this period helped popularize a term we still use today. In 1947, a moth was found in a relay of the Harvard Mark II. Grace Hopper taped it into the logbook with the note, "First actual case of bug being found." Engineers had used bug before, but that story carried bug and debugging into everyday computing language, and errors in programs became known as bugs. Back into the story. The ENIAC's success was thanks not only to Eckert and Moschly, but also to the ENIAC 6, six brilliant women who programmed the machine and developed techniques that shaped early software, even though their contributions weren't fully recognized at the time. As the decades passed, computers became more reliable. In the late 1950s, transistors replaced vacuum tubes. They did the same job but were smaller, faster, and far less prone to failure. Then, in the 1960s, the integrated circuit, a chip containing many transistors, revolutionized computing again, sparking a boom in California's Santa Clara Valley. The silicon at the heart of these chips gave the region its name, Silicon Valley. At first, these early integrated circuits could only perform a single function, like adding or subtracting. But as designs improved, engineers redesigned them to handle multiple tasks at once. Eventually, nearly all the main functions of a computer were placed on a single chip, called the microprocessor. This invention shrank computers from rooms to desktop machines to laptops, and finally into devices we can carry in our pockets. Today, your smartphone has more processing power than those early giants, the room-sized ENIAC included. It's like going from a rowboat to a modern flagship in just a few decades, or, for anime fans, from a rowboat to the Thousand Sunny. We've charted the evolution of computers through time. Now let's open one up and see what makes it tick. From the earliest tally marks to today's smartphones, computers have changed shape and speed, but their essence is the same. They take in information, transform it, remember it, and share results. This rhythm is the information processing cycle, IPC. Input, processing, storage, output. We need to peek inside the machine that performs this cycle. Let's meet the fundamental pieces that make a computer work. The physical hardware and the guiding software that together carry out each step of the cycle. Every generation made machines faster, smaller, and smarter, until we arrived at the modern computer. But what exactly is inside this marvel we use every day? A computer, much like a human body, is a system of coordinated parts. Hardware is its physical structure, the parts you can touch, and each component supports one or more steps of the IPC. At the center lies the central processing unit, CPU, often called the computer's brain. It fetches instructions, decodes them, and executes them with relentless precision, billions of steps per second, making it the heart of all processing. Beside it is RAM, random access memory, the computer's short-term workspace where active programs and data live. Think of RAM as the ship's deck. It's where all the real action happens. Think of it like the straw hat crew on deck during a fight, only the members needed for that moment are up and active, while the rest stay below until they're called. In the same way, RAM holds just the data and programs the CPU is using right now, ready for quick access. However, RAM has its limitation. Being electronic, it needs a constant supply of power to retain data. When the power is cut, everything stored disappears, making it a volatile form of memory. And when it fills up, the system slows down because it has to reach back to long-term storage more often. That long-term store is secondary storage, hard drives or solid-state drives, the vault that keeps your files and programs even when the power is off. You can picture it as the treasure chest where everything important is locked away for the long haul. Documents, photos, videos, games, all of it stays safe there. Around these core parts are input devices, like keyboard and mouse or like scouts delivering precise instructions to the captain, which is the CPU in our case. And microphones are like a transponder snail, carries spoken orders. Those types of devices are the senses, bringing information in. Output devices, monitors, speakers, printers, that send results back out. Without all these parts working together, the machine would sit in silence. But hardware alone is lifeless without instructions to follow. Software is the set of rules and programs that tell the hardware what to do. We usually group software into two broad types. System software, especially the operating system, organizes everything. managing memory, scheduling programs, and talking to devices, so the CPU always has work queued up, like a conductor guiding each section of an orchestra. Application software is what you use to get things done. Browsing the web, editing videos, writing documents, drawing, playing music or games. Without system software, nothing else can run. Without applications, the computer has no particular task to perform. Working together, system and application software guide the hardware through every step of the IPC, turning raw input into meaningful output. Think about it. When you tap on a YouTube thumbnail, the app makes the request, while the operating system talks to the hardware to stream the video smoothly. All these parts, the hardware and the software, give the computer the ability to sense, think, remember, and respond. But even with all its components working together, there's still one challenge: communication. The machine has its own way of thinking, as we humans have ours. Think about how people communicate with each other. We rely on language. Words give shape to our thoughts, turning something invisible inside our minds into something others can understand. Without language, two people might gesture, point, or draw symbols in the sand, but it would be slow and filled with misunderstanding. Language gives us precision. In the same way, to communicate and unlock the true potential of computers, we also need a language, a way to turn our ideas into instructions the machine can understand. Between you and the machine lies language. A computer's native tongue is machine language, long sequences of ones and zeros called binary code. It's precise but painstaking, like writing an epic adventure story using only yes and no. To bridge human thought and machine execution, we created programming languages. They translate our complex thoughts into something the machine can understand. Now, let's see how information is represented. To see how information is represented, consider number bases. Humans usually count in decimal, base 10, using digits 0 to 9. Computers operate in binary, base 2, using 0 and 1. To make binary easier to read, programmers sometimes use hexadecimal, base 16, with digits 0 to 9 and A to F. It's a shorthand that keeps the same meaning but fewer digits to juggle. The representation changes, the meaning does not. Since computers only understand zeros and ones if we want to give order to our computer directly, without using any kind of bridge, only God knows how many zeros and ones you will need to convey the most basic information. Now imagine you have to pass a whole set of orders to your computers. You can see that it's not conventional for us to be writing in binary to communicate with our machine. That's why humans created a special kind of bridges called programming languages. They serve as bridges that translate our complex thoughts into something the machine can understand. Once we learned how to speak to machines, the next question was what to say. If programming languages are the bridge between human thought and machine understanding, then what crosses that bridge is a program. A complete, structured set of ideas turned into action. Every time you write code, you're not just using a language, you're giving form to intention. You're shaping logic itself. A program is a set of precise instructions that tells the computer exactly what to do step by step, without room for confusion. If you've ever followed a cooking recipe, gathering ingredients, mixing them in order, and baking at the right temperature, you've already acted like a programmer. The computer, however, is the most literal chef in existence. It follows the recipe exactly as written. If one ingredient or step is missing, it won't improvise. It will simply fail, often spectacularly. You could say that a program is the will of the programmer carved into logic. Every app, every game, every website you've ever used began as a program, a list of human ideas transformed into machine action. Just as humans speak in different tongues, English, Japanese, Spanish, programmers use different languages to communicate with computers. Each programming language has its own grammar, style, and personality. Some programming languages, like C or assembly, are compiled, translated into machine code ahead of time. They speak directly to the hardware, fast, precise, but unforgiving. Others like Python or PHP are interpreted, read and executed line by line. They are gentler and more flexible, focusing on clarity and creativity. They let you describe what you want without worrying about every low-level detail. And some languages, like Java or C# blend both approaches, using a mix of compilation and interpretation. Think of programming languages like the different types of hockey. Each gives you a distinct edge: armament for strength, observation for awareness, conquerors for control. You can learn more than one, but mastering even one deeply can make you formidable. Similarly, you don't have to learn every programming language to become a great developer. Mastering one with understanding and intent can be just as powerful. Once you grasp its logic, you start to see the patterns shared across all others. No matter the language, they all share the same goal: to translate human thought into the binary rhythm the computer understands. When you master one, you don't just learn to talk to machines. You learn to think logically, creatively, and precisely. Every programmer is also an artist, shaping invisible ideas into something you can see, touch, or play. Becoming a programmer isn't about memorizing syntax. It's about learning a process, a way of thinking. Every creation, from a simple calculator to a full game engine, follows the same rhythm. Step 1. Define the problem. What are you trying to solve? What are the inputs, and what should the outputs be? Step 2. Develop an algorithm. Break the task into smaller logical steps. Use plain language, diagrams, or even pseudocode to map your thoughts. Step 3. Code the program. Now translate your plan into the syntax of your chosen language. This is where ideas begin to take shape. Step 4. Test and debug. Run your code. Look for bugs. Don't fear them. Even the ENIAC 6 faced errors every day. Debugging is how you train, how you sharpen your craft. Step 5. Refine and maintain. Once it works, clean it. Add comments, optimize, and prepare it for future versions. Every program, like a ship, needs upkeep if it's going to keep sailing strong. And remember, this process never truly ends. Each project becomes a new adventure. Each bug, a clue to something deeper. That's the joy of programming. Endless growth through curiosity. So when people ask where your coding journey begins, tell them it doesn't start with syntax. It starts with curiosity, the same spark that lit humanity's very first count. From counting with stones to coding with silicon, we've been on one continuous voyage: the human desire to extend our minds beyond our bodies. Programming is simply the next chapter in that story. When you write code, you're doing what every great inventor, navigator, and dreamer has done before: turning thought into reality. You can build tools that help others, design worlds that live inside a screen, or automate tasks that give people more time to live. With code, imagination becomes structure, and logic becomes magic. So whether you're here because you love anime, technology, or just pure curiosity, remember this: the moment you start learning to program, you've eaten the code know me. You've gained the power to reshape your digital world, one line of code at a time. Now, it's your turn to awaken that power. The code know me awakened.